Hello, I'm Jovana Dakic. I'm ECR number 9 from the InnoDC project, and today I'll be talking about my research, tools for analysis of novel concepts of transmission systems for offshore wind power plants as part of Deliverable 2.5. Regarding the table of contents, I'll be talking about the project and its objectives, followed by the optimal design of HVAC transmission systems and comparison with the HVDC, low frequency transmission analysis, and at the end, conclusions and future work. The target of the project is to develop a tool for technical economical comparison analysis of the different scenarios, including all aspects as technology, efficiency, reliability, and availability of components, as well as minimizing the power losses and minimizing the costs. As we all know, there are different types of transmission systems for connecting the offshore wind power plants, like HVAC, HVDC, and a new proposed technology, low frequency AC. In the combination of AC or DC offshore wind power plants, we have different scenarios that could be analyzed at the same time, technically, economically. Therefore, at the end, we can do a final selection of the optimal design of starting from the offshore wind power plant to the shore. At first, I started analyzing the HVAC transmission system as the most traditional one, and this configuration is consisted of two substations, offshore and onshore, and interconnected with XLPE cables. The substations include power transformers, switch gears, and reactive power compensation. But not only the reactive power compensation is located on the substations, there is another location that is proposed, which is in the middle of the cable. Therefore, we have 5 proposed locations of reactive power compensation, and based on that, we have combinations of models with different locations of power compensation, and we have combinations with 1 to 3 reactors. About the HVDC transmission, the proposed technology is symmetrical monopole configuration, which is consisted of 2 VCEs interconnected with DC transmission cables. The converters are connected through transformers to the AC side, and the transformers are modeled the same as in the HVAC configuration. The transmission systems are modeled for steady state analysis in order to calculate power losses. The transformers are presented in the form of an admittance and impedance, which are calculated through copper losses, iron losses, short circuit voltage, and open circuit current. The preferred transformer topology is based on 2 transformers in parallel on each substation in order to increase the power export availability, and the rated power of the transformer is at 60% of the offshore wind power plant nominal power. The cables are represented with an equivalent P-section through hyperbolic functions, which are proved that this formulation provides a higher accuracy than equivalent P-sections directly obtained from the cable parameters. So at the end, we have this graph, which is a complete model in order to calculate the power losses coming from the transformers and the cables. So now I'll be talking about the optimal size and allocation of the reactive power compensation. As I said previously, we have 15 combinations of different locations for the reactive power compensation, or either we can call them reactors. And the idea is to find optimal location and optimal size of the reactors. Therefore, we minimized the cost of the power losses and the cost of reactors as a single objective function. And we have some equality constraints and equality constraints that we should consider. The power losses, as I said, are coming from the onshore transformers, offshore transformers, and the cable. The cost of the losses are presented in this following formula, where TOF presents the lifetime of the offshore wind farm, C energy of the cost of the energy in euros per megawatt, and we have here power losses times PW, where PW presents the probability of that wind speed to occur. So J presents the number of wind speeds that the wind farm is operating. It is important to say that we included that the offshore wind farm was operating at different wind speeds. The cost of reactors are presented with the following formula: K times the admittance of the reactor plus P, where K and P are coefficients derived from different cost functions, and they depend on where the reactor is located, onshore, offshore, or in the middle of the cable. About the constraints, we have equality and inequality constraints, where equality constraints are dependent on the power flow equations, and inequality constraints are limiting the voltages and currents in the nodes. So the voltages are limited from 0.9 to 1.1, and the current is limited to approximately 1.1 usually. And we have the also constraint that the delivered reactor power to the grid, or as we know, cosinus phi, is limited from 0.95 to 1. About the methodology, so first we have the initial definitions that we put in the tool, which are rated power of the onshore wind power plant, the transmission distance we want to analyze, and the main grid parameters. Based on that, we also can define our HVAC transmission voltage. In this case, we checked 3 transmission voltages. And based on all this information, we can calculate the parameters of the system. We further move to the optimization, which is based, as I said, on multiple wind speed conditions, and we analyze all voltages and all combinations of models with different locations of reactors. At the end, the calculation is done. We are adding the fixed costs, and in total we have total cost of the HVAC transmission system, and based on that, comparing for each power and each distance, we have an optimal location, optimal number of reactors, and the optimal voltage. At the end, we added HVDC transmission system, and we did the calculation of the total cost of that system, where that offers us that at the end we can do a final selection between these 2 transmission systems. So to talk about the results, there's different kind of ways to use this tool. One way is to get these 2 figures, which represent, I will say, like a final map where we show the break-even distance between HVAC and HVDC. So for X number of distances and epsilon number of powers, we can determine for each power and each length which is the voltage, or first, which is the transmission system that we should apply, or it is advised to apply, and after, which voltage of that transmission system is advised to be used. So we see here that we have a break distance around moving from 120 to around 180 kilometers, depending on the power and of course depending of the distance. Regarding to the second figure, this presents that how many reactors do we need, and we can see the swipe from having 1 reactor to having 3 reactors, and at the end turning into the HVDC technology. The second type of analysis that we can do with this tool is a single case study, having 1 transmission distance and 1 power of the offshore wind power plant, which will be showed further in MATLAB. Here I'll be presenting the single test case optimization for a rated power of 2.4 gigawatts and transmission distance of 120 kilometers, which is actually planned for a project in UK in the North Sea named Hornsea 3. So we run the code single test case and we let it run. While that, I will explain again from the methodology what is the idea. So we are testing 3 voltages, 110, 150 and 220, and all combinations of models with different reactor locations. The idea is to determine the optimal HVAC configuration, and at the end compare it to HVDC to finally decide which transmission system is more suitable for this rated power and this transmission distance. Now we will see the graphs, how they look like. The first idea from here, what we will get is the combinations with one reactor, two reactors, and three reactors, and the comparison between them, and to see by the cost of objective function what would be the most optimal one. Here are the results that come out from this code. So as I said, 3 voltages, all possible combinations and possible locations of reactors, and we're comparing the cost of the objective function. As we see, having 3 reactors, which are combinations from C10, C11 to C15, is the most cheapest ones and the most optimal ones compared to the cost of the objective function. And here C13 seems like the optimal configuration for this offshore distance and offshore wind power plant. Later on this, we should now compare, because this is only cost of the objective function, we have to add the fixed costs or to calculate the total cost of the system in order to determine the optimal voltage. Now here on the left side, we have, as I said, C13 as the most optimal configuration with possible reactor locations. And we have the comparison of 110, 150, and 220 kV, where the yellow box represents the substation cost, and the green box presents the cable cost, and the blue the cost of the losses, and the red the cost of the reactors. So from here we can see that 220 kV is the suggested voltage as a suggested optimal voltage. And what we can see that here the total cost of the cables, which is the green color, affects the most the total cost of the optimal design for HVAC configuration. On the left side, we have a comparison with HVDC, and in this case we have like that HVDC costs around 1,800 million of euros, while HVAC for this particular power and this particular transmission distance is around 1,600. So in this case, we the suggested transmission system would be HVAC. Now we move on to low frequency transmission analysis. So here is presented the model of the low frequency transmission system, which is actually very close to the HVAC system, but we have additional element, which is the back-to-back converter, which is usually consisted of 2 MMCs, and is used to convert the low frequency on the offshore side to the grid frequency, which is usually 50 or 60 hertz. So here we have transformer parameters, cable parameters, the converter parameters, and the grid parameters. And the converter parameters are presented with phase reactors and two Thevenin equivalents. The equation representing the converter losses is actually the power coming inside the converter minus the losses that are happening in the MMCs, which are represented with the loss coefficients and the current passing through the MMCs. It is equal to the power that is leaving the converter on the onshore side. What is different in low frequency systems than in HVAC systems due to the lower frequency actually is we have some system modifications and improvements and also a bit of flowbacks. The first change is in the low frequency cables. Due to the lower frequency, we have reduced charging current and actually more space for active current, therefore the cable ampacity increases. Also we have the resistance and the skin effect. So due to the lower frequency, we have less skin effect, and therefore the resistance decreases, and therefore the power losses in in cables operating a lower frequency are less. The other change is in the transformers, where the volume of the core of a transformer working at lower frequency is bigger. So cost of transformers are higher, and therefore cost of the substation platform, as the transformer for low frequency is located at the offshore side. On the other hand, core losses are smaller, so we will have a little bit less power losses also coming from the transformers. The main, we cannot call it flaw, but let's say a bit disadvantage is back-to-back converter is a bit expensive because, as we said, it's consisted of 2 MMCs. It is almost equal to having an offshore and onshore and offshore converter, as in HVDC system. And this cost function for my model is determined from different official projects as ABB or Alstom. The results for this part of project are not yet done, so I will explain you the targets of this analysis. First, I will talk about which frequency we are using to represent the low frequency AC transmission system. It is usually taken that is a 16.67, which is 1/3 of 50 Hertz. Why this frequency is used is usually because this frequency is used in railway systems, so it is kind of a proof technology or kind of already used frequency that can be tested also on offshore wind farms. And the target is to finish this analysis and compare it with HVAC and HVDC systems to see where are, or is it possible that there is a break even distance where we can fit this low frequency system. The next move is sensitivity analysis of the cost data. So the sensitivity analysis of cost data is, as there are many main components that are contributing to the total cost of the system, as the converter, of course, first, the cable cost and the cost of power losses. By changing their costs with some sensitivity factors, we can see the change in the total cost and see the changes in the comparisons. The third point would be finding the optimal frequency. So swiping different low frequencies or frequencies lower than 50 Hertz to see which actually frequency is optimal. And at the end, the idea is to have a complete tool for comparison of HVAC, HVDC, and low frequency AC, and actually choosing the optimal transmission system. About the future work, which will be also one of the hard tasks, I believe, is there is one key point that will influence also a lot the total cost of these transmission systems, which is reliability of the transmission systems, which must be included, as there will always be some energy not served to the shore due to the availability of the components. The next step, as I said, was also including AC and DC offshore wind farms. So completed with the cost and losses analysis and, of course, reliability included, we will have a complete system or a complete tool starting from the offshore wind farm, or the beginning of the offshore wind farm, to the shore. We will have a complete view of all elements and what brings the losses and what is the most main components of contributing in finding the both technically and economically optimal choice. The third future work which is planned is stability analysis as well, which is actually also going to contribute to the power losses again and again to the cost at the end. So there is we are considering to include dynamic constraints included in the tool, so that the tool will be totally complete from all aspects. Thank you for your attention, and for more detailed explanations and any questions, please contact my email, and thank you very much once again.